She's a remarkable explorer, and of course exploring is our theme. That's why we're here, that's why we're having this meeting. She's a wonderful scientist, as we're about to find out, and person. And I'm very glad to say she is a fellow geologist, and I keep telling her, this is the friendliest audience you will ever encounter. I think that's probably true. She has a remarkable history. She went to undergraduate school at Stanford, where she majored in earth science. She did a really unusual thing. She was a varsity athlete playing championship NCAA Division I women's rugby. It's true, I guess, huh? She earned her PhD in geology at UCLA, studying surface geologic processes, large landslide mechanisms on both the Earth and Mars using the remote imaging we have now from the Martian satellite. She's received many academic awards and honors. As a postdoc after UCLA, she went to Caltech, where she collaborated on the Mars Science Laboratory on the Curiosity rover and was intimately involved in the rovers on Mars. She became an astronaut trainee in 2017, completed her training as a member of the Artemis group of astronaut candidates. She was assigned as a mission specialist on the SpaceX Crew 4 mission. So since she was here last, she's traveled 17,000 miles an hour for 170 days. Pretty cool. She returned from that in October of 22, and we're extremely lucky and thankful to have her here to give us an update on what she's been doing and excitement. We know she will be deeply involved in the future of the exploration of the solar system, and we're all going to be watching because we all expect to see her doing some really cool things. So, safe travels, and thank you for coming back to see us again.
Thank you so much, Dr. Lund, and thank you all so much for having me here today. I am super excited to be here and to share with you all a little bit about my mission that Dr. Lund just mentioned, the 170 days on the International Space Station, and also to talk a little bit about how what we're doing on the ISS is impacting our plans for future lunar exploration. So let's see if we can get this going. Great. So this first image here is kind of a metaphor for what I'd like to talk about. This is a picture of the moon that I took out the cupola window. So the cupola on the ISS are the set of 7 windows that open up to the world, the Earth rotating below. But also outside the cupola, we can see into the night sky as well. And for me, the Earth is absolutely gorgeous, and we'll get into that. But for me, the moon really stole the show. And so, I think as we kind of look to the moon from the ISS, there's an important metaphor about how we can use the ISS as a test bed to help us develop technologies and understand operations and science that will help us on the moon. Let's see. Here we go. So the first kind of few ways that the ISS can be used to help pave the way to the moon and eventually to Mars are technology demonstrations. So this one here, you can see I'm wearing a kind of a large vest. This is what's called the Astrorad vest, and it is a prototype that with the intention of protecting a crew member from radiation. And the idea is that something like this could enable the crew member to continue working and still be agile and active, but be protected from solar radiation. And so it's these types of tests where we're pushing the boundaries of understanding how we can protect our crew members as we go out further and further into the solar system. Another test that we did here is one that's called X-Roots. So here we are growing plants, growing crops on the ISS. And in particular in this experiment, we are working to grow crops without soil. So we're using hydroponic and aeroponic techniques to grow these plants, because we understand that, of course, soil comes with mass and volume and containment constraints that might pose an issue as we go out further into the solar system. And so we're working on technologies like this that would help enable that in future, for future exploration. Last example of a technology, here I'm working on some called surface avatar, but you can see my right hand, I'm working with essentially kind of a robotic arm. And in the top left, you see a screen that I'm actually looking at the robot on the ground that I'm controlling from the ISS. So I'm using my hand to maneuver the robot on the ground in a conference room like this. And so this type of technology, these types of advanced robotics will be really important as we start to think about kind of a sustained presence on the moon, which is what we're talking about with the Artemis program, and being able to operate from within a gateway type of environment where we're working from environment onto a different surface. But of course, the most important thing to me, and probably to you all in the room, that we are able to transfer from the ISS is the way that we do science. So you see here in this is a view through the cupola, and I have a Mars geologic map that I brought up with me. So I, as Dr. Lin mentioned, I am a geologist and a planetary geologist by trade. And so most of my work, both in graduate school and actually really just in graduate school, was focused on using the remote sensing assets that we have in orbit around Mars to help create maps like this, where we're mapping out the geology of the surface of Mars by really looking at it from an orbital perspective. In particular, we have high-resolution images like this of a place on Mars that's called Valles Marineris, is a giant canyon in the equatorial region of Mars. And my research was looking at some landslides and surface processes that occur in this canyon. But you can see how we can use the high-resolution imagery as well as our composition data, thermal inertia data, et cetera, to do some really great science on the surface of another planet using these orbital assets. And so it's really neat for me, coming from that perspective, then on the ISS, to be able to do something similar. So to be able to see the Earth, this is the photo, again, that I took out of the cupola window. And so to be able to see the Earth, this is the Grand Canyon in comparison to Valles Marineris on Mars. Very different scales, but really interesting to make that comparison for myself as an analog. And to be able to see the Earth from that kind of orbital perspective in a very similar way to the way that we do planetary work is particularly interesting because, of course, on Earth, we're able to go to those places and put boots on the ground and do in situ field work. So here's actually, this is my classmates, my astronaut classmates that were selected with me in 2017, and we are doing some geology training. So we actually get a few weeks, I think it's about 4 weeks total of geology training as part of our kind of basic training when we come into the astronaut corps. And then, of course, the Artemis astronauts will get a significantly increased amount of geologic training, much like the Apollo astronauts. And so, of course, being able to stand in the Grand Canyon and be able to, kind of marry those two types of data sets, both the field work in situ with that orbital perspective, is exactly what we intend to do on the moon. We'll be able to use the high-resolution imagery and composition data sets that we have from LROC and others to be able to really map out our traverse paths and then be able to put boots on the ground and put those two pieces together. So I'm really, really excited about the future that we have ahead of us and the ways that we can use ISS to inform that future exploration. So before I step away, I just want to show a quick video of our mission highlights. Let's see if it will. So our mission starts out with about a year's worth of training, both at Johnson Space Center here in Houston and at Kennedy, at Hawthorne with the SpaceX facilities. And then all that training leads us to Kennedy Space Center, where we launch from. So we see our rocket, Falcon 9 rocket with our Dragon capsule on top. We were able to cross the crew access arm, leave the suit room, the same suit room that Dr. Schmidt was able to depart from, and then board the rocket. This is an absolutely phenomenal launch. In the middle of the night, we were told it was gorgeous, but it was gorgeous from our perspective as well. Pretty amazing to feel the G's come on, and about 8 minutes later, we are in low Earth orbit. And the ISS appears kind of out of the blackness of space, this place that you know is your home for the next 6 months. We came in for a rendezvous and docking, come in a little bit hot to give our friends a hug, but that was the beginning of our ISS expedition. And so, of course, the reason that we go to the ISS, this orbiting laboratory, is to do science. And so you see us here doing material science in the glove box. I'm doing some combustion science. We do fluid dynamics, all looking at what happens when we remove the gravity vector from the equation. How do fluids behave? How do our bodies behave? Speaking of which, we do human research where we become the test subjects ourselves, looking at the effect of long-duration spaceflight on the human body and brain. Here I'm doing cell biology, and then we also can use the external environment of the ISS to do science. So we can pack the Japanese airlock full of CubeSats, essentially, and then launch them into the space environment. And then these are more of the technology demonstrations. So you saw there some more advanced robotics that can help crew members, and more footage of us participating in the X-Roots experiment. When we're complete with all that science, we're able to take samples, preserve them on board until it's time to return them down to the ground via visiting vehicles like these. So we had a Cygnus, a Progress, and a SpaceX Dragon come to visit us while we were on board. When a vehicle comes on board, we quickly remove as much of the cargo as we can because we're waiting to get to that. Fresh food is absolutely a treat on board. And the neat thing about SpaceX Dragon cargo vehicles is that we're able to return stuff back to the ground. So we can return those samples, things like failed hardware that needs troubleshooting, and can get returned to the ground. We also were visited by the Boeing Starliner. There's the first successful rendezvous of the Boeing Starliner vehicle, which was very exciting. And then, of course, we had some fun while we were on board as well, taking advantage of the microgravity environment. Here, I think we're doing our favorite superheroes. I'm being Spider-Woman. But really just very neat to be able to see, fundamental physics at work, how water behaves differently, how air functions within inside a water sphere that forms. Pretty neat. Of course, while we're on board, we also have to ensure we are exercising to maintain our bone density, muscular strength, and cardiovascular strength. So that's a big part of our day. And then nutrition as well. You saw there my crewmates made me a birthday cake while I was on board. It was absolutely delicious. But food is the center of community on board, just like it is here. This is the cupola that I mentioned, so you see those windows opening up. And here I am doing that scientific observation process that I mentioned, where I'm looking at these features and marrying them up with our expectation from the ground. We got to see some absolutely gorgeous views from the cupola, getting to see all of our favorite places on Earth. And then, of course, the night sky is just as gorgeous. We had some absolutely phenomenal aurora while we were on board. But after 170 days, it was time to return home. So we said goodbye to our colleagues, handed over the keys to station, and departed. Our return trip was pretty quick. It was actually the quickest return trip yet by a U.S. spacecraft from the ISS. And so we were screaming across the West Coast, coming to off the coast of Jacksonville. And when you're careening through the atmosphere, the most beautiful sight you can see is this: 4 good parachutes. We splashed down in the Atlantic Ocean. First crew to do that since Apollo 9, actually. You can check us on that, Dr. Schmidt. And SpaceX recovered us quickly and brought us back to Houston, back here to Ellington Field. That was the first time we were able to say hello to all of our family and friends who'd been holding down the fort while we were gone, and who helped enable the mission to be a success. So it's absolutely absolutely fantastic mission, but one of the things that definitely stuck with me during that time was of course the privilege of being able to be a part of that mission, to have that opportunity, but also to be part of such an amazing legacy. So this photo is actually inside the cupola. It's just kind of underneath the windows. And the inscription essentially is telling you that this is an Apollo 11 lunar sample that was taken up to the summit of Mount Everest by Scott Pierzynski, and is put in place here with Summit Rock as well, on display in the cupola. And so for me, that was just a reminder every time that I went in there of the legacy of Apollo through to the ISS, and then on, of course, to Artemis and future exploration to the moon, and then eventually to Mars. So just a real privilege to be able to be a part of it. Thanks.
Repeat the question.
Sure. The question was, what is the impact of the weight of water when we were trying to make trades in terms of the upmass of soil? And so one answer to that question is that we are able to recycle our water. So on board station, at least, the way we operate, we are able to recycle, I believe, about 96% of our water, all the fluids on station. And so we're able to purify it, filter it, and then drink it the next day, use it the next day. And so those types of processes, those types of technologies will then become useful, so you're not having to resupply that water.
How early in the process of your visits to the moon are you going to start trying out different construction processes and materials to maybe build a permanent base?
Yeah, it's a good question that I'm not sure I know the answer to, partly because I'm not sure it's been fully worked out yet. We are definitely still in the process of ironing out what each of those missions will look like, what each of those mission objectives will be, and how the science will fold into that as well. And some of the hardware is part of that discussion as well, when we'll have a rover available, which of course for the Apollo missions was a huge impact in terms of the science that we were able to accomplish. So we're looking forward to having that come online, and that would always be a trade, between that science and that architecture. Yeah, absolutely. The question was about the crew complement, what consists the crew complement on board the ISS, and how international is that crew. So for us, there were 7 of us total. So there are 4 of us that are members of the Crew 4 mission, so that launched from Kennedy together on the SpaceX Dragon. And within that crew of 4, there are 3 NASA astronauts, so myself, Bob Hines, and Chell Ingram is our commander. And then our 4th member was Samantha Cristoforetti, so she is an Italian astronaut through the European Space Agency. So we were the 4 that kind of made up the U.S. segment, the U.S. half of the ISS during our mission. And then while we were up there, we joined with 3 cosmonauts who were residing in the Russian segment. So they came up on a Soyuz vehicle, Russian Soyuz, and there are 3 cosmonauts. That complement shifts. It definitely shifts. I guess they just came back. The crew after us, Crew 5, their Dragon crew had a Russian crew member as their 4th member, and we flew an American on a Soyuz vehicle. So there's a swap kind of between those 2 seats that currently is how we operate. But at any time, we also, of course, have our international partners on the U.S. side, so the European Space Agency, as I mentioned, the Japanese Space Agency, Canadian, I'm missing one, and now UAE as well. We have UAE astronauts as well. And so the mixture between those varies depending on things that are above my pay grade.
Any adjustments? Was there anything that you noticed that was different?
Yeah, so the question was any physiological changes over the course of the mission. And so there definitely, I'm an N of 1, but and our whole sample size group is pretty small in terms of compared to the general population. But so there is definitely some variability in terms of people's experience. But for me, I did not have any lasting effects from being on orbit. Nothing that, when we return, the countermeasures that we participate in, the exercise that we do, really does enable us to be very strong and fit. In some cases, stronger and fitter than we were when we left. It just is a few days to a few weeks of kind of readjustment to gravity, getting your neurovestibular system back in order, but your muscles and your cardiovascular system are actually really still set up for success.
Final comments. Thank you, ladies and gentlemen, for your questions. And I know we could go on quite a bit, but we'd like to get final comments. And one thought, maybe, if you want to think about in the final comments, the Apollo legacy and Artemis, and what are the lessons from Apollo? What are some of the things that Artemis can take from Apollo? What, Jack, would you say from Apollo you think would be helpful to Artemis? It'd be interesting to get your two thoughts, because we're so fortunate to have the baton pass here. So, Jessica, would you like to go first?
Sure. So yeah, just to respond to your prompt, I think we certainly, as we are ironing out, exactly how we're going to do operations back on the moon, and understanding all of these kinds of questions that have come up in terms of how do we manage dust? What do we need the suits to be able to do? What do we need our crew members to be able to do? Do we need to improve our tools, and if so, where? Kind of all of these questions. There's a real concerted effort to try not to reinvent the wheel, and to really lean on the expertise of people like Dr. Schmidt and the other Apollo astronauts, and really use that as a launching point, no pun intended, to help us go back to the surface, to stay. And for this audience in particular, the first thing that comes to mind in terms of one way that we're doing that is through our geology training. I mentioned it briefly, but the Artemis astronauts, they start lunar training next week, I believe, for the Artemis 2 crew that has just been announced, who will go around the moon and come back. And that has been a huge push from the scientific community, from the operations community, to ensure that all of our astronauts get substantial amount of geologic training, so that we are able to send anybody out to the surface and expect reasonably that they're going to be able to make observations, make interpretations, make deltas to the plan as they see fit, much like Dr. Schmidt and his colleagues did. So we're even going back to a lot of the same training sites, going to Iceland, to New Mexico, a lot of the same sites that you all spent time to do that similar type of training. So we're leaning heavily on the legacy and super excited about the future.
Do it from right here.
As we all know, here at GCAGS, HGS, AAPG, we try to come up with really creative speakers gifts. And Charles and Linda and I discussed this for a long time. I hadn't bought a new rock hammer in years. And they make great rock hammers with still S-wing. And they have a great description on the rock hammers now. Forged in one piece of American steel. They also decided that the pick end of the rock hammer is so dangerous it has to be coated in rubber. So I don't know what we're going to do with that. Anyway, we decided that in the tradition, or I guess the concept of Apollo handing off to Artemis, we would give Jessica and Jack a new rock hammer. We hope she can take it to the moon. I'm afraid it's too heavy, but we could hollow it out or something. And we wanted to have them, they are both inscribed Apollo to Artemis, GeoGolf 23. So this is our speaker gift, and we are so grateful you're here, and you are an inspiration to our profession.
I might just gotta talk a little about rock hammer.
The only difference between this and what we had on the moon in terms of basic concept is that we had a chisel point. And we actually had a chisel on the moon, which I never used, and in my current work, I really regret that. Because there were some samples now that I think we could have done much better with the chisel than we did with the rock hammer. But I tell you, the sedimentologists taught me that a chisel point is a very useful thing to have, and I think many of you probably have chisel point hammer. It's a lot better for digging. And thank you very much.
Thank you.
Wait,